Today we're going to add on to what we did last class, where we did mole-to-mole ratios. Today we're going to take the mole-to-mole ratios and we're going to add them into longer, more complicated problems. So, for example, this is something that you saw yesterday. How many moles of a product, in this case it is aspirin, can be produced through the following reaction, where salicylic acid, or I'm going to refer to this most of the time as just SA, and acetic anhydride are reacted to produce aspirin and something else. Okay, how many moles of aspirin are produced by 75.0 moles of salicylic acid? So why don't you pause this, and you should be able to do this based on what we did in class last time. So pause, give it a try, make sure you set it up okay. So the first thing that I see is that the moles of aspirin and the moles of salicylic acid, those aren't the same compound. So my wanted compound is not the same as my given compound, which tells me immediately if my wanted compound, CMPD for compound, is not equal to my given compound, that tells me that I need to use mole ratio. Because mole ratio, remember, is the only named conversion factor that we have so far that converts from one compound to another compound. Everything else is within the same compound. So I can come up with a plan here. I know that I'm going to use mole ratio. And this is kind of where I always start. All right. I want to find moles of aspirin, which is C9H8O4, and that's going to come from moles of salicylic acid, or SA. Okay, so when I look at this, I see its dimensional analysis, and I see that I can do it in one step. So question mark moles aspirin equals 75.0 moles salicylic acid. And then I'm going to put my moles of salicylic acid on bottom. And I know that this conversion factor is going to be a mole ratio. So I can do moles of C9H8O4. And the coefficients from here, or the numbers from here, come from the coefficients in the balanced chemical equation. Okay, so I go through and I look at this and I notice, hey, everything is very nicely balanced. So this is just 1 to 1, which means that I make 75.0 moles of C9H8O4. Now that's all well and good and everything, but we're not going to be counting out moles of something, right? That's not a really useful thing for us. So it's far more likely that we're going to be measuring like a mass or a volume. So for example, I could ask you what mass of aspirin is produced. Well, I just figured out how many moles, so man, do I have anything that converts between mass and moles? Moles of mass? Mass and moles, molar mass. All right, so I'm going to use molar mass to convert from the moles of C9H8O4 to the mass of aspirin. Now, this problem just says mass, okay? So sometimes I'll specify what unit I'm looking for, sometimes I won't. And if I don't, I want you to just pick the easiest one possible, okay? So for this one, I'm going to go with grams of C9H8O4 because molar mass is in grams per mole. So that makes it nice and easy. All right, and again, I notice this is one single dimensional analysis step. It's one conversion factor, nice and easy. So why don't you take a second and see if you can correctly calculate the molar mass of C9H8O4. Oops, a daisy. Don't want to do that. So the molar mass is 180.159 grams C9H8O4 over 1 mole C9H8O4. Okay, and if you're curious about how I got that, you should probably go back and review molar mass, but it's 12 times the molar mass of carbon plus 8 times the molar mass of hydrogen plus 4 times the molar mass of oxygen. So again, this is one step, so I can do question mark grams C9H8O4 equals our answer from before, 75.0 moles C9H8O4. I'm going to put my moles of C9H8O4 on the bottom to make sure they're in the right place. And then it's molar mass, so that's going to be grams C9H8O4 on top. 180.159 goes there, and 1 mole goes there. My moles cancel out, and I'm left with, hey, grams of C9H8O4, which is exactly what I'm looking for. All right, so now I plug it into my calculator, and I get 1.35 times 10 to the 4th grams C9H8O4. Okay, and I'm going to be using 3 significant figures in my answer from this 3 significant figures of the moles C9H8O4, which comes from this 75.0 moles of salicylic acid. Now remember, these mole ratios, these are counts, right? So these are going to have infinite number of significant figures. And this molar mass has 6 significant figures. So as long as you're not rounding your molar masses and doing something silly, they shouldn't limit your number of significant figures, because you should have lots of significant figures in molar masses. Okay, so let's now think about what this allows us to do. All right, so the key here is my mole-to-mole ratio. That allows me to convert between moles of a known and moles of an unknown using mole ratio. Now I can do all kinds of stuff from this, right? I saw that I could use molar mass to get to grams of the unknown, UK, unknown. I could do that, right? I could go from, maybe on this side, I could come from, maybe use Avogadro's number and start with particles, right? I could take this grams now, and I could go to milliliters using density, right? There's all kinds of fun, cool, interesting places that we could go with this, and you will be going with this. But the key, oops-a-daisy, the key here is recognizing this, that if our wanted compound and a given compound are not the same, we need to use a mole ratio. All right, so let's take a look at this problem, at a problem in action. All right, so here we go. We have sodium azide reacts to form sodium and nitrogen gas. This happens in airbags. This production of nitrogen gas is what inflates the airbag so you don't smack your face on the steering wheel. Okay? And I have, the question's asking if 0.500 moles sodium azide reacts, what mass in grams of nitrogen would result? So there it is. Here's my given compound. Here's my wanted compound. They are not the same. So I'm going to have to do, I know I'm going to have to do a mole ratio. Okay? And that is going to convert from my given compound, which is sodium azide, to my wanted compound, which is nitrogen, moles N2. So I'm going to get the numbers from that from the balanced chemical equation. Oh, but hold the phone. I look up here and I notice that this isn't balanced. Okay, so let's balance. This is a good time to balance. I'm going to fix the nitrogen first. So I see there are odd-even disagreement. So multiply sodium azide by 2 and nitrogen by 3 gives you 6. So it should be 2, 2, 3. Now, am I given moles of sodium azide? I'm looking here, right? Am I given that? Yes. Am I given, or am I trying to find moles of nitrogen? No, I'm trying to find grams, mass in grams of nitrogen. All right, what do I know that converts between mass and moles? Well, just like the last problem, that was molar mass. Okay, and that's going to get me grams of nitrogen. Now, looking at this, I can see that this is all-dimensional analysis, and I can do it all at the same time. All right, so I'm going to show you that first. So question mark grams N2 equals my given, which is 0.500 moles sodium azide, which I'm going to immediately put on the bottom. Okay, now I'm going to take a pause. I am going to, according to this problem, I am going to be doing, moles, mole ratio here. So this is going to be moles N2. And then once I have my moles N2, I'm not done yet because I'm trying to find grams N2. So I'm going to be using molar mass. So I'm going to put my moles N2 over here, and I'm going to start canceling some units here. And I'm going to put my grams N2 up here. And that is what I'm looking for. All right, so as long as I get everything to work here, I should end up with mass in grams of nitrogen. So the first thing I'll fill in the numbers from my mole ratio. So that's 3 moles N2 to 2 moles NaN3. And then this is 28.014 grams N2 to 1 mole N2. And again, I'm getting that from the periodic table. And so when I do this calculation, okay, I'm going to end up with 3 significant figures from this number. Okay, so it's 21.0 grams N2. All right. Now, I could do this in 2 steps if I really felt that that was necessary. All right. So I could go question mark grams, or no, not grams then. If I'm going to do it in 2 steps, I'm going to break it up and go moles N2 equals 0.500 moles NaN3. And then I do a mole ratio. And moles N2 on top. And then fill in the numbers 3 to 2. And that's 0.750 moles N2. And then I could do question mark grams N2 equals 0.750 moles N2. And then I can do 20, here, let's do this in the correct order. Put my moles N2 on the bottom and my grams N2 on the top. So that stuff cancels. And I do 28.014 grams over 1 mole. And when I calculate it out, 21.0 grams N2. Now, is there really a huge difference between these 2 different methods? No. However, if you do the 2 steps, like this bottom, when you get to this step here where you calculate an answer, remember, you don't round for significant figures until you have a final answer. So do not round when you plug the number in over here, okay? This method is a little prone to rounding errors, all right? And again, like I really like the way the top gets set up because it sets up nicely for your calculator. You use 0.500 times 3 divided by 2 times 28.014. Nice and easy. Your calculators can handle that simply, okay? So I kind of like the top method better, but if the bottom method speaks to you, go ahead. Space things out, all right?